All right. So I started talking about transformers, real transformers. I wanted to kind of recap a little bit from last time, but then kind of talk about the model that we tend to use when we talk about a transformer in a power system. All right. So when I say in a power system, in the grid, I think a transformer is really for two uses. Either it's in the grid or it's in some kind of power electronics thing. All right. So when I say some kind of power electronics thing, like if you think about your last homework on problem 2, where you had the data sheet for the core, that would be inside of a power electronics device, which we'll talk about that stuff towards the end of the semester a little bit. But in the power system, there's some specific ways that we tend to think about transformers that we're going to go through. All right. So I want to recap first. All right. So real transformers. All right. So I already wrote down here the two things that make the transformer real, I guess. So first of all, I've shown where the flux is here, right? With the way that I have the two currents going, I1 and I2, they push their flux in the same direction. Okay. The fact that I say this is a real transformer is to say two things. The fact that the mu is not infinite, okay, and the fact that there's losses in this guy. Okay. So when I say that, if the mu is not infinite, right, what does that mean about what the flux is doing? Is my image for the fluxes here correct? In other words, that dashed line that I have, is that a correct image? Well, it kind of is. Not entirely, right? What's true if my mu is finite? There's somebody used the word fringing. There's leakage, right? So some of the flux would be leaking out of the core and would look like that. And this guy would have his own leakage. All right. So when I draw those pads there, in other words, some of the flux is leaking out, is what we call that. Fringing kind of deals with if I have an air gap. It's supposed to be the case that the field jumps across the air gap, but some of it kind of bulges out. That's what we call fringing. Yeah, if mu is finite, basically it just means that some of the fluxes, the term we use is leaking. All right, but the basic idea here is that for each of these coils, right, there's sort of this flux that links both coils, and then there's the leakage, right, that goes with it. Now, the other piece of this is really the fact that there's losses, and there's losses in the windings, and there's losses in the core. All right. I don't fully expect you guys to understand all the losses in the core, but I gave you two of the reasons for it, right? One is that I've got these magnetic domains that are moving around. What's the other reason why there's losses in the core? Conductivity. So there's magnetic fields going through this iron material, right? That's going to create currents inside there, right? Because changing magnetic fields create currents. We don't usually worry about the details of that other than to say that there's losses. When I said there's losses, what that means is some power that's going to that primary is getting bled off somewhere. And if I touch a transformer, it's hot as a result of it. All right. So we end up with this model where I have the right N2 over N1 times I2 right there. Now, one thing, let's kind of note a couple of things here. So what I've added in this real transformer, RP, RS, and R core. Okay. RP and RS are winding losses. Okay. So if I think about this just intuitively, tell me about how big you think RP and RS are going to be. I say winding losses, I mean there's copper windings, and so that's basically the copper resistance, right? They should be small, right? They should be small because we're talking about the resistance of a wire, which is very hard to put a number on because it's very temperature dependent. Okay. Our core, how about that? Large or small? It should be fairly large, because if it was small, that would mean that what would be true? So first of all, this thing over here, these are not two inductors, right? This is an ideal transformer. if our core was a small number, what would be true about the current going into the primary? Well, a lot of it would go into this path, right? And ideally, what do we want to have happen? If this was an ideal transformer, what would change about my picture? If this was an ideal transformer, what would be true about L leak 1 and L leak 2? They would be 0. There'd be no leakage. Those guys would be 0. There'd be no losses. So RP and RS would be 0. Okay. What about L mag right there? Well, L mag, if I had an ideal transformer, L mag, if I think I've got the summary, not in these slides, but in the other slides. L mag, how do I relate that to the reluctance of the core? So if I have first of all, if I have an inductance, how do I relate that to reluctance? Okay, so yeah, N1 squared over the reluctance. Okay. What's going to be true if I had an ideal transformer? What would be true about the reluctance of the core? So if it's ideal, our mu is infinite and our reluctance is 0. This guy would be infinite. So what's that mean? It basically means if this thing were truly ideal, this guy would reduce himself to just the ideal transformer. Right? L mag would be infinite, which means that it disappears from the circuit, right? Why would it disappear from the circuit? Because it'd be infinite impedance, right? And our core, it would also be infinite if it didn't exist. Okay. All right. So this guy reduces to that. Now, help me with this. Why is this current going this direction? N2 over N1 times I2. Why does it go in the direction that it's going? Because it is. I2 is flowing into the dot. So I1 or this. So my notes here, I refer to this as I2 prime, right? That guy is flowing out of the dot. I2 is into the dot. I2 prime is out of the dot. Okay. This current is not necessarily the same as I1. That's the effect of this guy being non-ideal. Okay. All right. This is the equivalent model that I went to last time. All right, where I basically used, and this is summarized in that transformer applications. If I have an impedance over here on the load side, I can reflect that over to the secondary by multiplying it by the turns ratio squared, like that. All right, it is not hard to prove that I can move those over there. I did a little bit of a proof of it last time. But that leads to this thing here, which is sometimes called the T model, right? Because it looks like a T. If you at least if you forget the ideal transformer hanging off of it, it looks like a T. All right. Now, the thing I did last time, which was kind of weird, right, was I basically said, I can move that branch, that parallel branch with XM and RC, I can move that up to the front. Now, why is that the case? Basically, what I'm saying is, what did we argue already about the value of these guys and the value of these guys relative to each other? What's true about those impedances? You guys said that if I had an ideal transformer, L mag was going to be what? L mag would going to be really big. If I had an ideal transformer, it would be infinite. And what would L leak be? 0. Right? So the reality is that these guys are small and these are big. Right? So if I think from the perspective of, what the current would be going through here, I could do some impedance analysis to tell me that there's not going to be very much current going through that branch in the middle. Right? But there will be, whatever current I have here, hopefully is going here. Intuitively, that should make some sense because the idea of a transformer is I want the power to go from the primary to the secondary. So this guy right here, this magnetizing and this core stuff, ideally, I don't want much current to be going through those branches. Okay. There's some current going through there to keep the flux going, but that's it. Okay. All right. So the thing I did last time where this is unfortunately this is where you guys have learned how to solve weird circuits and you're used to specific numbers for everything and you solve everything to 4 decimal points. That doesn't work with most power system stuff, right? No one says that the resistance R1 is 2.4892864 ohms, right? They don't say that because it's different by the time of day based on how hot it is, right? These are very small numbers and they can change very significantly. No one knows the reluctances of these things perfectly, and they usually don't need to. All right, the model is helpful for us to think about things, but we usually don't typically have the numbers. So really what we usually do is there's a set of tests. So if Duke or any utility or something like that, if they want to understand the parameters of their transformers, then they will have the vendor that they buy them from do a set of tests on those. And I talked about this last time, the open circuit test and the short circuit test. All right. The open circuit test, you put a voltage on the primary and you leave the secondary open circuited. And the short circuit test, you short circuit the secondary, which is potentially a bad thing. Short circuits usually aren't fun, right? So notice the thing I said here is I apply rated current at the primary and short circuit the secondary. All right, basically to try to keep things okay, I need to make sure that I'm applying less voltage than normal. All right, so if I just look theoretically at what I've got here, right? So this is the open circuit test. And I called this VOC and IOC. All right. If I look at this situation right here, if my secondary is open circuited, how much current do I have I2 prime right here? How much current will be going into the primary of the ideal transformer? 0, right? So this guy is going to be 0. So all of my IOC is going where? All of my IOC is going into this guy and this guy. All right, so the way I would write this, so I wrote IM is the magnetizing current. That's the current in the inductor. IC is this current in the core loss. If I think of IOC as a vector, or as a phasor, right? How could I write that in terms of IM and IC right there? What would be the real part and what would be the imaginary part? Yep. Just a KCL says IC plus IM. IM should be entirely imaginary. IC should be entirely real. So this guy basically becomes that. Okay. So if what we typically do when we use this test is we measure VOC. So we say, what's the magnitude of VOC, right? We say, what's the magnitude of IOC? And we say, what's the POC? Where's the power loss in this scenario? Where am I losing power? Which component? R sub C, right? Because there should be no current over in this branch, right? So I basically have VOC squared divided by RC, like that. So however much power I get when I do that. All right. Here's the short circuit test. All right. Hopefully you can see why I don't apply the same voltage in this case, right? If I applied the full rated voltage, I short circuit would end up being a pretty big current here. All right. And so what I end up doing is if you actually do this test, what you do is you basically start out with a variable source and VSC starts at 0 and you slowly increase it until ISC gets to be the rated value. Right? That's how you actually do it. But let's just see if we can rationalize this, right? Now, if I put a short circuit on here, I2 is not equal to 0, right? There's going to be some current, right? So the way that how would I deal with this? How do I simplify this circuit though? What do I know about V2 in this scenario? It's got to be 0 because I got 0 volts across that. I just did, and that comes from doing a KVL around this loop right here. Okay. So what's that mean about VP? It's also 0, right? So that tells me that the circuit model reduces to, here's VSC. And here's that parallel branch. Okay. And here's these two guys. Now, I wrote out these values here, R1 plus this reflected value of R2 and X1 plus this reflected value of X2. I'm going to call this REQ, and I'm going to call this XEQ. All right, so this is REQ, and this is XEQ. Equivalent is what the EQ is for. All right, now I put a short right there. Now, what have we said is true about the values of these sort of leakage parameters? So this X, this guy here, and this sort of winding loss. What's true about those relative to RC and XM? They're much smaller. So if this guy is going to be a small impedance, these guys are going to be big impedances. Those three impedances are all in parallel, right? So if they're all in parallel, if I have small impedance in parallel with big impedance, what does that become? Especially if they're orders of magnitude different, right? If I had, let's say, 1 kilo ohm in parallel with 1 ohm, all right, so that's a parallel setup here. If I had 1 kilo ohm in parallel with 1 ohm, what do I have? Yeah, pretty much 1 ohm, right? It would be, yeah, probably 0.999 or something like that, but so small that the difference would be pretty negligible, right? So basically what we do in that test is I basically say I've got this scenario here, right? So my current is only flowing through REQ and XEQ. All right, so that's why I sort of summarized here. The open circuit test gives us RC and XM, and the short circuit test gives us these other two guys, the REQ. So this guy's the REQ and XEQ. All right. So problem 2 on the homework kind of goes through this analysis. Now, last time I went through this example, and it's entirely worked out in that set of notes, transformer applications. This was the example transformers, 8,000 volt to 240 volt. And this guy had a rating of 20 kVA. So you'll notice I pretty much always give you these two numbers when I deal with the transformers. I give you the rating of the transformer, and I give you the voltage rating. When you buy a transformer, it doesn't come with a turns ratio, right? It comes with a high voltage side rating and a low voltage side rating. And the reason for that is there's standard voltages that they operate the grid at, right? And they have to design the insulation and things like that to be able to be rated for the right voltages, right? So if they weren't designed for the right voltages, there'd be the wrong insulation and stuff would fail. All right, so we don't, that 8,000 volt to 240 volt tells me basically what my turns ratio is if I want to use that. Okay. So basically I said these are the results I get. And notice V short circuit is a lot smaller than V open circuit. V open circuit was the rated voltage, 8,000 volts. V short circuit, much, much smaller. All right, to be able to make sure that my short circuit current is the rated current for it. And you could see that, right? If you did the math, 20 kVA, how would I get the rated current? If this guy's 8,000 volts and 20 kVA, how do I get the rated current? Yeah, I rated for this guy would be 20 kVA divided by 8,000 volts, which I think if you do that math should work out to 2.5 amps. All right, would be the right number. Okay, that's the primary side current. There's also a secondary side current. What would the secondary side current be? In other words, 8,000 volts on the primary, 2.5 amps on the primary. Secondary is 240 volts. How much current's going to be over there on the secondary? More or less? A lot more, right? How much more? 8,000 over 240 more, right? That's how much more, right? The turns ratio relationship would tell us how much more. Okay. All right. So I went through this last time, and these were the numbers that I came up with. All right, 160 kilo ohms for R core. XM is that value there. REQ is that. XEQ is that. Now we don't typically talk in terms of the actual inductances. We talk in terms of the reactances, right? The impedance values. So if I did want to find LM, so the magnetizing inductance, how would I find the magnetizing inductance from this? What's that? Divide by omega. And unless you're told otherwise, omega is always basically 2 pi 60. All right. I guess if I was trying to be a jerk on a test, maybe it would be 2 pi 50 or something like that, just to see if you're paying attention. All right, but for the most part, the world only has two frequencies, 50 and 60 hertz. Okay. So usually everything's in 60 hertz because that's the North American standard. Okay. All right, so I end up with those values. Now, the thing is, some of you guys that are really kind of exact people, right, should be probably bothered by the fact that I went from this picture to this picture and said, hey, that's fine, right? Because again, like I said, that would, if you did that in circuits 2 with Yahoo, you would have lost some points for sure, right? That's I can't just move impedances somewhere else. Now, why does that work? It works because R1 and X1 are small numbers. All right, so one of the things that I did, just to, for those of you that care, right, I ran the numbers and said, you know, it's really hard to separate out R1 and X1, but they're usually about half of those equivalent impedances, right? That's usually about the case. All right, if I ran the numbers, if I did it this way, what I did was I just ran a real quick test and said, okay, if I had this set up here, open circuited, the current that I would measure going into this thing would be 0.2135, and the power would be 398.79. Here's the percent error between the 400 amps, or sorry, the 400 watts and the 0.214 amps that I gave you here. Right, so the values, the differences between what I would get with this model and what I get with this model, negligible, right? And that's why we make that assumption, and we can make that assumption. Right, it's just based on the sort of typical values of the parameters. All right, questions about that? It's not that exciting. Okay, all right. Bottom line is, once I really get into dealing with stuff in a power system, usually if this is and this is what I end up using with the equivalent circuit, and you'll see some different things. Like sometimes you'll see people, and this one of the things gets confusing. You look in different textbooks and things like that, you'll see sometimes REQ and XEQ are on the other side, right? They might be shown here. Both of them are wrong, but they're both pretty damn close. All right, it's one of those things. If you're an exact person, it will bother you. All right, but it comes from the approximate values of these two things. All right, this is the equivalent circuit model that we use. But the bottom line is, how much current's going through this path right here? Typically, usually that's the case. All right, when the transformer is fully loaded, there is very little current going through this pathway. And when I say fully loaded, what I mean, and we're going to get to some examples of this here. When I say fully loaded, like if this was a 20 kVA transformer, right? Fully loaded means how much power is passing through this transformer? 20 kVA, okay? So if there's 20 kVA passing through the transformer, we just said that means there's 2.5 amps going into the primary. If you think about this guy, 2.5 amps in the primary, I don't know, if I ran through the numbers right here for how much current is going through this branch, I didn't do the numbers. When this guy's at full load, this is 2.5 amps going in here. If I did the numbers real quick, if this was 8,000 volts, 8,000 divided by the parallel combination of these impedances, we're going to be talking like tens of milliamps. Okay, or hundreds of milliamps. So it really doesn't matter. And so what that leads to is when I'm getting into a power system, all right, I basically use this model right here. I forget about that other path, and I just look at this REQ and the XEQ. Those are typically the only things that I know about the transformer. Okay. All right. And we're going to use that here in a little bit. All right. But I want to look at, basically when I talk about transformers in the power system, the example, probably the best example, there's all kinds of transformers out there, right? There's big transformers that you would see in a substation. So if you ever driven by a substation, there's big blocks that are there. Those are transformers. Those guys are usually dealing with much higher voltages. Okay, so the transformers I've shown right here, these guys here are what you see on top of a pole. All right. So what is this 25 number right here, do you think? It's 25 kVA. All right, we're going to look at some examples today that I stole from Duke from some locations. So 25 kVA is a pole mounted transformer. And these are pole mounted transformers. So when I look at these things right here, let me see if you can figure this out. Where's the high voltage side? Where's the low voltage side? Can you guys tell? It's just a can, right? If you look at this, I don't know, it's probably labeled over here, right? This is the high voltage.
Oh, so once it comes like out the power lines, is there still like a high voltage, like a 230, and it steps it down to like 25?
So the example I'm going to use it is basically, this could be about 20 kV. All right. So if I look at the way that the power system works, maybe I should do this, right? So as I go from the generators, that might be getting about 20 kV. And then it goes through a transformer, and I'm making a one-line diagram without ever explaining what that is. But 20 kV goes up to like either 230 kV or some number like that on the transmission grid. And then it goes down to different values, but let's say maybe 23 kV. That's what a lot of Duke Carolinas uses, is 23 kV. So 23 kV is when you're driving down the road and you're watching those wires overhead, it's going to be 23 kV probably going into these high voltage taps, we call them. And then on the low voltage taps over here, we'll have 240 volts coming out if it's going into a house. All right. So first of all, if I have all these, let's think about over here. Here's your house at 240 volts. All right. So we're going to see today, what's Duke model your house as? Well, they're going to say it's 6 kV or 6 kilowatts. All right. So that's about your peak load. So where's that 6 kilowatts come from? There's no losses in this system. There's 6 kilowatts going to your house. How much is coming out of the generator if there's no losses in the system? 6 kilowatts. Now it goes through 1, 2, 3 transformers to get there. All right. So what's going on is I go from 20 kV to 230 kV. There's 6 kilowatts in, 6 kilowatts out. What's true about the current on this side versus this side? As I go from low voltage to high voltage, what should be true about the current? Current goes down. And then it goes back up again. All right. By the time I get back here, it goes back. It gets quite a bit higher. Why did they go up in voltage and down in current? What's good about that? Yeah, because as I have a current flowing through this wire has some resistance. The losses in that guy are I squared R. So we want the I to be as small as we can get. Ideally, it'd be 0, right? They'd love to get it to infinite volts, right? But that doesn't make sense. Okay. You get as high as you can. All right. What I'm showing here, these are pole mounted distribution transformers. And without getting too complicated, what I would see on this side here is basically 240 volts. All right. So it's got a little cutaway here that I took from Eaton off of one of their data sheets, right? So you can see inside here, here's our core with the windings on it. Okay. And the high voltage stuff has these things on it called bushings, which are basically insulators, okay, for protection. This one here is the one I see more commonly when I look around. Is this guy here where there's one tap. Any idea what I mean, this is going to be on a test, so you can stop paying attention if you want to, but I got 20 kV here. Why do you think this guy has the 2 heads sticking up and this guy only has the 1? Yeah, this guy right here it would be line to line, like this would be A and B phase, whereas this guy probably just has A phase going to it. This is the one I think I see more commonly. All right, you can see all kinds of stuff. It depends on the utility. It depends on all sorts of stuff. Okay. But look around, and this is the one I see the most common off the Duke system. Okay. All right. So anyway, the most important thing usually is what are the voltage ratings, and then what's the power rating on the transformer. All right. So like I said, if I'm operating this guy at rated current, usually we say that this here doesn't really matter. Right? At rated current, I1 is much, much greater than, I should say magnitude of I1 is much, much greater than the magnitude of IE. And so the picture we make is this one. Okay. All right. So this is the picture that we get for this particular transformer. The thing that matters to me, V1 is here, right? I call this VP. So the voltage on the primary of the ideal transformer is always going to be lower than the magnitude of V1. And I should be careful, always assuming that power is going to the load. All right. As I was saying, the world's a changing place. And so sometimes the power might actually be going this way, right? Because there could be some distributed generation on that secondary side nowadays. Okay. All right. Questions about that?
Would there be like a phase shift? If V2 had angle 0, would there be a phase shift?
V2, you're going back to the homework question. V2 and VP should never have a phase shift between them. Because if I look at this, right, my ideal transformer, what's my relationship for the voltages? VP and V2 here, how do they relate to each other? VP over N1 equals V2 over N2. That tells me those phases have to be the same. Now, how do I know? It's a good question. How do I know that those two phases have to be? This cooked some noodles, I think, on the homework. Yeah, so if I look at this, I'm basically saying phasor 1 equals phasor 2 times a constant. What angle does a constant have? 0 degrees. Now, a constant could potentially have a negative value, but N1 and N2 are integers. I mean, they're positive numbers. They have to be pi. I can't have a negative number of turns. So it's always going to be the case that VP and V2 are going to have the same angle. Now, V1 over here is probably going to have a different angle because there's a current flowing through that impedance. Okay. All right. Yeah, that was, I said problem 5 last time was really a circuits 2 problem at its core. All right. It wasn't too much of a transformers or magnetics problem, but it was a tricky problem. All right. It's a harder problem than you would have had probably. I know how when we do those problems in circuits 2, we always say, well, V2 has an angle of 0, and then you work everything backwards from there typically, right? I made that one a little bit trickier. Okay. All right. Let's look at an example here. All right, so let's say I've got a 25 kVA transformer, 2400 volts to 240 volts. Now that's a pretty common distribution transformer as well. 2400 volts is not unheard of that you would have on a distribution system. And this guy has REQ equal to that number and XEQ equal to that number. Now again, I just said earlier, you don't have numbers like that typically. Well, I just gave them to you anyway. Now we're going to see what I typically give, which is a little bit different than that. All right. But let's say those are my numbers. And let's say the load on the transformer is 2.304 ohms. All right, so how do I draw that? All right. What I want to figure out is the voltages and stuff. So basically what I'm going to say is in this case, I'm gonna say I got 2400 volts. And then I have REQ, XEQ. And then here's my ideal transformer. Okay, and then I put my load on here. My load is 2.304 ohms. And let's say, ultimately, I want to figure out a couple of different things. Say I want to figure out I1, and let's say I want to figure out V2, and I want to figure out I2. Okay. Now, where should I start with this? What's the easiest way to go about it? Well, I don't need to know anything about the rated currents in this case. I've been told I want to figure out I1, I2, and V2. All right, those are the three things I'm trying to get to. I don't need to get rated current. I want to get whatever I1 is, actual current. Do what? Use Ohm's law. No. Good. So if I want to deal with this, there's two ways to go about it, right? What you just said, if I used Ohm's law, basically there's a voltage across here. That voltage is not necessarily going to be zero. In fact, I know it's not going to be zero, right? One way I could do this is I could look at this guy and I could say, well, let's do the analysis and say, figure out what basically include the transformer in this analysis and go through and figure out what I2 is going to be. And it's a kind of a clunky setup. One thing I said last time is what's true about this impedance over here, this load that I put on here. What can I do with that load? How can I treat that load in my analysis? So I can reflect that across the primary, right? So I talked about this last time. I said, if I have a transformer, I said, here's V1, here's I1, and here's a load on this guy. Z load, right? Here's V2, here's I2. From the perspective of the primary, what I can say is that V1 over I1, if I were to solve it, ends up being whatever Z load is times N2, times N1 over N2 squared. What I call that is the reflected impedance. All right. So what I can do is I can simplify the circuit by reflecting the impedance over. Now, again, there's a couple of ways that I could do this. I could basically go through and I could do this kind of multi-step process and do a KVL around this loop and a KVL around this loop and then combine those two equations and blah, blah, blah. Or the simpler thing is basically to use this reflected impedance. All right. In other words, this is the impedance that I see looking into this. So what I can do is I can redraw the circuit. So here it is, right? This is REQ. This is XEQ. I can redraw this circuit and say, again, I'm going to say I've got, what did I say, 2400 volts here. All right. I can redraw this circuit with 2400 volts. REQ, XEQ, and basically put the reflected impedance over here. I'll call it Z1, like that. All right. So what would that Z1 be in this case? Well, I said the reflected is the turns ratio squared times whatever load impedance I have. Okay. So what's my turns ratio? Because again, I haven't said what the turns ratio is, right? I said, yeah, it's 10. It's the high voltage rating divided by the low voltage rating. That's how they give it to you. So basically this is N1, this is N2. That doesn't mean that there's 2,400 turns and 240 turns. It just means that the number of turns has that ratio. All right, might be 10 turns on one side and 1 turn on the other. All right. Again, we don't know those details. We don't care about those details. So they give them to us this way. All right. So, all right, Z1, what is that value? Well, it's N1 over N2 squared times 2.304. N1 over N2 is 10 in this case. So what is this equal to? If it's 10 squared, yeah, it'd be 230.4. All right. Higher impedance on the primary side when I reflect it over, because the currents are going to end up being smaller. All right. If you're comfortable with that, you can kind of think that through. Right. So if I want to figure out what is I1 going to be, well, that's what I can solve for in this circuit, right? What would I1 be? Given what I have here, give me an equation. So from the bottom circuit here, give me an equation for I1, the phasor. And let's say, to make everybody happy, let's say this is 0 degrees. Right. $2,400 over the sum of the impedances. So tell me the sum of the, how do I write out the sum of the REQ, XEQ, and Z1? How do I write that out? REQ plus, yeah, the impedance reflected over is entirely real. So I'd say plus 230.4 plus J times XEQ, right? Because that's an imaginary part of the impedance. Well, so from the perspective of this circuit right here, the ideal transformer is gone. Basically what I've done is I've mapped the effect of the secondary onto the primary. And again, you go into the notes that I posted from last Wednesday, and I do the derivation that shows how you would get to that relationship. Okay. All right. So basically it's like I've removed the secondary entirely and I've just reflected it over. Okay. All right. So I come up with a value for I1 from that. All right. So when first of all, tell me a little bit about this guy. Is this current going to have a positive angle or a negative angle? Intuitively, you should be able to answer that. A negative angle, right? Because it's an inductive circuit, right? So this guy better have a negative angle, right? So what do I work out with? If I do the math, I get 10.3106 negative J 0.2907. Okay, like that. All right, so that's my current I1. All right, now, what did I also say I wanted? Well, I said I wanted V2 and I wanted I2, right? So how should I start that? Well, yeah, there's a couple of ways. So let's start with I2. How could I find I2? What's that? Yeah, how could I find I2?
I1 over N1, or I1 N1 is equal to I2.
Yeah, so basically what he just said is use the ideal transformer relationship, right? So what do I have for my ideal transformer relationship? Well, again, what I say with the ideal transformer thing is the magnitude of I1 times N1 equals the magnitude of I2 times N2. And I don't like negative signs to scare me, right? What do I know about this case? There's a current going into the dot. So what about the other side? It's current out of the dot, right? So basically these guys, I don't need to worry about the magnitudes like that. In other words, they're going to have the same phase. Okay. So what's that tell me? That tells me if I get I2 is basically going to be I1. I can write this in terms of my phasors times N2 over N1 like that. All right. Yeah. So what's oh yeah, I'm dividing. Yeah, sorry. So it's sorry. N1 over N2, yeah. Let's do it this way. Yeah, so it's N1 over N2. Yeah, which is basically, I don't even think, I1 over 10. No, I1 times 10, sorry. I1 times 10. In my brain, I think of it this way, right? The low voltage side has the higher current, right? It has to, right? So I don't even know, I don't even really think about the N2, N1. What I think of is it better be the case that there's 10 times as much current on the secondary as there is on the primary, right? And that's what I look for when I'm trying to check myself to see if I'm correct. All right. So if I do that, I get that I2 equals, if I have this 10.3106, what's I2 going to be? 103.106 minus J times 2.907. All right, just factor of 10 higher. Okay. All right, now, what if I wanted to figure out what is V2? Well, I could do it that way. It should be the case that V2 times 2.304, I2 times 2.304 would be V2. Let's not do it that way though. I got another way to do it.
V2 squared over N1.
Well, so how could I get it from looking at this circuit right here? Yeah, so the voltage across here, voltage across Z1, where is that voltage in this circuit above it? VP. All right. Once I have VP, then I do exactly what you were saying, Joey, and I can then take that and transform it over to the other side. So how would I get VP in this circuit right here? KVL, right? And so I would say that VP is equal to whatever 2400 volts minus I1 times REQ plus JXEQ. All right, if I do that math, what I end up with is 2,300. I guess I wrote 2.3756 times 10 to the third minus J times 66.974. And this guy has units of volts. Okay. As I did. Yeah, I don't know. Either way it works. But that's the way I did it. Right? How would I get V2, the voltage that I was looking for? Well, so not the same, almost the same. Divide by 10, right? Divide by the turns ratio. So it would basically be 237.56 minus J times 6.6974, like that. Now, if I took this, right, and I did V2, if I did that V2 divided by 2.304, which is what I said was the load impedance, I would end up getting what I got by doing the reflection. All right, it would end up being the same result, except I do it in one step. All right. So in reality, oftentimes you know, what we do is we try to reflect that load over, and then we go through this analysis. And as you see in power system stuff, if you take power systems, we don't typically think of our loads as impedances. We think of our loads as powers, right? Duke doesn't say your house is a certain impedance. They'll say your house is a certain number of kilowatts. All right. Yeah, Cody.
So define VD,
Define V what?
the Voltstone primary,
Mhm.
we also just go to multiply I1 times V1?
Yeah, you could also say I1 times Z1. That would work as well, because that's just a statement of Ohm's law. That would work. Yeah. So yeah, that's probably an important point to make. I'll say it's also equal to I1 times that Z1. Right? Those would be equal to each other. In my mind, I always think of it that way. One thing I always look at is in the traditional way of operating a power system, this voltage closer to the load is always going to be lower than that voltage. All right. Because I know that there's always some impedances to the network, which makes the voltages reduce if current flows through it. All right. So I don't know. My brain thinks of it that way. All right. All right. Questions about that? All right. Now, this is not correct, right, for all the currents, because what have I done here? What have I not done specifically? What did I throw out? I threw out that magnetizing branch right there and that core loss, right? So I basically said they're so small that they don't matter. All right. Now, that's a totally valid thing for me to do in most cases. All right, because those currents are awfully small. All right. So one more thing that we're going to do is, I'm not going to spend a lot of time on it because I find it to be confusing, but it's important to introduce what if you take Power Systems 1 next semester, I guess it would be. What you will find is a lot of use of this per unit system. All right. Basically, in real power systems, nobody says that they apply 480 volts or 120 volts or 4160 volts. They say I apply 1 per unit voltage. Okay. All right. And basically, when the way I think about this idea is you're used to in electronics 1, electronics 2, circuits, whatever. Some circuits you're applying, 12 volts, sometimes 24 volts, sometimes 5 volts. We don't deal with that in power systems. There's only standard voltages, right? So at every outlet in North America, there's 120 volts. All right. If I'm going to hook up outlets, so these guys here, these lights, they get 277 volts. All right. The motors in this building get 480 volts. All right. There's a standard set of voltages that we use. And so what we say is if I'm going to hook a motor up to the grid, I hook it up to 100% of the rated voltage. Okay. If the motor is rated for 480 volts, I'm saying I'm hooking it up to 100% of its rated voltage. And we think of everything per unit's a funny way to think of it. It's basically percentages of the rated voltage is what it means, right? So we tend to talk about things in percent of rated voltage. All right. So, and I use the 2 examples here. So I keep using these 240 volt transformers because 240 volts is what we consider a house to get. All right. So 240 volts is what I'll consider to be my 100% rated voltage. All right, that would be the 100% rated voltage that I give to the air conditioner, let's say, in my house. All right. Now, why do we do this? Because there's all kinds of reasons you can kind of come up with, but it's a lot easier to talk in terms of percentages to people than to talk in relative values than it is to talk in absolute values, right? Like what I was saying about these, like REQ and XEQ, right? 2.1858 and 6.5573 ohms. Those are weird numbers, right? But I can talk about those in terms of a percent value. And so it turned out that almost all transformers have about the same percent impedance. All right. And I always have, it's also common to say for things like a motor, if I hook a motor up to any, and it doesn't matter what value of motor, If I hook a motor up to 80% of its rated voltage or less, the motor does not like that. It is not rated to operate that way. It doesn't matter if that's a motor that's connected to a 4160 volt system or 120 volt system. All motors are designed to operate with at least 80% of their rated voltage. Okay. So for that reason, if you talk to a power systems engineer, they talk in terms of per unit values. Okay. So what this does is it gives us kind of a, when we look at a certain part of the power system, I have to convert all the voltages and currents that I have in volts and amps and ohms into that per unit system. Okay. So what I get is I have an apparent power base, I have a voltage base, I have a current base, and I have an impedance base. Okay. And so the way that I think about this is if I talk about a voltage in per unit, right? What I do is I take that voltage and I divide it by V base. Okay. So if I had for myself a 480 volt system, right? If I apply 480 volts to a motor that has a base voltage of 480, I'm applying 1 per unit. All right. And if I have 1 per unit current flowing into a motor, then it's got its rated current going into it. All right. That's kind of the way that we think of it. It's a percent of the rated value. Now, this is easy to think about in terms of a power system. So I don't know, man, I'm probably not supposed to use this picture. This is a set of distribution circuits in Wilmington, North Carolina. And so what that basically, all those thick lines that you see on there basically are lines that they're power lines that are rated for about 24 kV. All right. And then I can zoom in on a section of that, and I did. All right. So I zoomed in on one little section of it. So this is a transformer right here. It's one of those, it's a pad mount transformer. So I say pad mount transformer, like if you go around the neighborhood and you see those green boxes. All right, there's a green box right there. And then this is a set of loads. All right, so kind of interesting to see this, right? So what I see here, down in here, is the way the utility would think about this. And what it says is that the transformer, the connected capacity, there's 9 customers and a connected capacity of 50 kVA. Okay, so that means that this transformer right here must be 50 kVA. And also one of the things I notice is that it's connected apparently to C-phase. All right. So it's a single phase connection to the grid, and there's 9 people, and those 9 people apparently have a connected capacity of 50 kVA. So that means that this is a 50 kVA transformer that I'd have. Okay. All right. So if I were to look up what the data would be for a typical transformer, the data is kind of goofy and kind of all over the place. This is sort of an example of a 25 kVA pole mount transformer. What I see in here is a couple of numbers. So it gives me an impedance in a percentage value. Okay. And I also notice that it gives me an efficiency value. So this guy says 98.95% efficient. And that would be P out over P in. All right. So you can calculate what that is, but it gives me the impedance as a percentage. All right. So let's look at an example. So I have this guy here. This is a 50 kVA transformer. It's pad mounted. His output is 240 volts. And what I'm going to specifically say is he's connected to 13,200 volts on the primary and 240 volts on the secondary. So what that means is I'm going to say that this little power system, so I can think of this little connection of 9 customers right here as basically being a little power system. And I'm going to say that the rated power is 50 kVA. That's going to be my base. All right. And the primary voltage is going to be 13,200 volts. And the secondary voltage is going to be 240 volts. Real typical residential stuff. Okay. So how do I figure out the base current, do you think, on the primary and secondary side? how would I figure out those values? Yeah, power over the voltage, right? So this would be 50 kVA divided by 13,200. And this would be 50 kVA divided by 240. Right? Those numbers are going to be drastically different. What are they going to be? This guy's going to be 3.7879 amps. And this guy's going to be a lot, 208.333 amps. Okay. Now, there's also, I get a base impedance value. How do you think I'm going to calculate the base impedance value? Yeah, V base over I base. So I'm going to say, so on the primary side, I would have 13,200 divided by whatever my I base is. So that's that 3.78 amps. Bless you. Yeah, that's going to be 3.4848 K ohms. And the secondary, it's going to be 1.152 ohms. Okay, that'd be 240 divided by the 208. Okay, now, one of the things I included here is for that pad mount transformer right there for 50 kVA, what's it give me for the impedance? Well, give me this, 1.67. Now, that's not 1.67 ohms. That's 1.67%. All right, 1.67%. That means it's 1.67% of the base value. All right, is what that means. So now, if I were to look up some standard values, all right, I said, you know, IEEE, they have different standards for what's expected. So people design into these standards here. One of the things I see, if I look at a 50 kVA transformer here, the normal range for percent impedance is between 1.2 and 6.4. All right, so this guy's in the normal range. All right, now the other thing it's telling me is that it has an X over R ratio. All right, what does that mean? Well, so it told me that the Z value was 1.67%. And oftentimes we write that as it's written right here, percent Z is 1.67. It's not ohms, it's 1.67. All right, and that's in percent. All right, what do you think X over R is telling me?
The imaginary part.
Imaginary part of the real part. So if I wanted to figure out Z in terms of R plus JX, I would have to get the magnitude of Z. And how would this X over R thing help me? Yep, do the cosine of tan inverse X over R, right? That would be R. And then, you know, I'd use the sine of that to figure out what the X is. Okay, so nobody knows what the values in ohms are for those things. These are values that we typically tend to use. And usually people, if you really look at what I'm giving you here, is this is numbers that people use when they're trying to figure out if there's a short circuit on that, right? Why a short circuit? Why would they care about that? Well, if I put a short circuit on my transformer on the secondary side, this impedance now matters a heck of a lot because it's the only thing basically keeping the gates of hell out, right? Is that there's some impedance that's left that's not zero to keep the current from going to infinity. All right, so it matters if I have a short circuit. Okay. Anyway, we're not getting too down in the weeds on that, but basically what I want to do is I want to say, all right, let's say this 50 kVA transformer is loaded with this Z load, and I have V1 equal to 13,200 volts. Okay. All right. And I said that this guy has a percent Z that was equal to, what did I say, 1.67. Okay. And I said that he has a, what did I say? I said, I'm going to use this recommended X over R. I'm going to say X over R is 1.6. Okay. All right. And I put this load on it right here. So as far as I'm concerned, the circuit I have is here's V1. Here's REQ. Here's XEQ. All right. Here's the ideal transformer. Like that. And here's ZL. Like that. All right, let's say I want to figure out I1 right here. Okay. What's the first thing I got to do? Well, I don't know REQ and XEQ, right? I just know this percent Z and all this stuff, right? How can I figure out what REQ and XEQ actually are? Well, yeah, so KVLs can help me get to I1, right? So what I want to get to is I probably want to do that reflecting thing again, right? Don't I? I want to say, I want to get this into, here's V1, here's REQ, and here's XEQ. And there's this reflected impedance, I'll call it Z1, right? This Z1 here would be ZL times N1 over N2 squared. Problem is, I don't have numbers for REQ and XEQ, right? What I have is this guy, percent Z, and I have my X over R. So help me out with this. Yes, I can map it to a real impedance by saying it's 1.67 times my base impedance. All right, so my base impedance, all right, I said that my Z base on the primary side, my Z base on the primary side here was 3.4848 kiloohms. 3.4848 kiloohms. And I said this guy has a percent Z of 1.67. Okay, so the magnitude of the Z, in other words, the magnitude of REQ plus JXEQ is what? 3.4848 kiloohms times not 1.67, but 0.0167. These are percentages, okay? So that's going to be some number, right? And if I wanted to figure out how do I get to REQ and XEQ, how do I get to those? Yeah, use that ratio, right? Yeah, so I basically say it's whatever the magnitude of Z is times cosine of tan inverse X over R. So in this case, that's 1.6. And this guy would be the sine of that. 1.6. All right. And if I do those calculations and I come up with those numbers, what I end up with is what? 30.8439 and 49.3502. Okay. Now with that, if I do the reflected version of the impedance, in other words, I just take this impedance here and I multiply it by the turns ratio squared, I've got everything I need to solve for I1 at that point, right? And I'll end up getting my I1 value if I go through that. Basically, it's going to be that 13,200 divided by ZEQ plus the reflected version of the impedance, which is going to end up being 2.9608 kiloohms plus J times 1.1702 kiloohms. And one of the reasons, I guess, maybe to Moose's question, Moose the leftist, but the reason I was using the real and imaginary part is like impedances are easier for me to think about. It's weird to think of a current in terms of its real and imaginary part, or voltage in terms of its real and imaginary part. But impedance is easy for me to think about that way. Okay. So if I end up solving for that I1, you guys can do that, right? What the number that I'll get here is, let's just say it's 3.7836 minus J times 1.542, oops, 1.5424, like that. If I said that in per unit, if I wanted that number in per unit, how would I get to that? So I said I1 per unit. How would I get to that, do you think? Yeah, I divide it by I base, right? So I express that as a percentage. So I say I1 divided by whatever I base primary is. And this ends up being, now let me ask you this is going to be a number less than 1 or greater than 1? Less than 1. All right, this guy's going to end up being 0.9989 minus J times 0.4072. Right, what that tells me is that this guy is basically pulling 99% of his rated current. Okay, right, and the way I could see that it's, if I took the magnitude of that, I1 per unit. This, now I'm jumping ahead, it seems weird. This guy is basically going to work out to be about, well, it actually, if I took this carefully, it's actually a little bit more than the rated current, right? I think if I put the number there, this guy would actually be, I don't know what it is. I shouldn't put a number in, but I'm going to say I think it's about 1.01 or something like that. That means it's drawing 101% of rated current. All right, and the reason I know it's a little bit higher is because I based this impedance here on what I took out of Duke's own analysis, where they were drawing a little bit more than rated power. And why'd they do that? Well, because basically, if you notice this, they're basically assuming it's the winter peak. They're saying, all right, what happens if everybody's heat pump's running and it's 6 o'clock in the morning and it's really freaking cold outside? So it was basically Christmas Eve, right? So it was Christmas Eve and it was really cold. It's probably doing a little bit more than the rated condition, right? So that's, and I don't know how they came up with that number, right? I mean, I kind of do, but it's on the basis of the number of how big a typical customer is. Okay. Anyway, that's it for today.